In 5.2, we are going to talk about power functions and polynomial functions. So a power function is of the form f of x equals k, some constant k, times x to some power. Now, k and p have to be real numbers. And remember, we call k the coefficient. So if we think about our original functions that we learned about, those parent functions, which one of these are power functions? Well, we could rewrite number one as x to the 0. So that is a power function. This one, x to the first, power function. That one's obviously a power function, power function. This one we could write as x to the negative 1. Guess what? It's a power function. This is x to the negative 2. It's a power function. This is x to the 1/2. Power function. This is x to the 1/3. Power function. So all of the functions that we see here are constant, identity, quadratic, cubic, reciprocal, reciprocal squared, square root, and cubic, or cube root, are all going to be identified as power functions. They all are, every single one of them. So let's take a look at these three here. It says, which of these are power functions? Well, we could combine those because of multiplication. That is x to the 5th. That's a power function. But here are two separate terms, not a power function. Now, it's the sum of individual power functions, but it is not considered a power function. So then this, way too complicated, not a power function. So the only one that is a power function is our first one here. Now, power functions are really interesting because if the function is an even power function, then both ends are going to be going in the same direction. Now, I want to just start with ones where the power is positive. If it's a positive even, then both ends go up or both ends go down. If it's a positive odd, one end will go up and one end will go down, and it will mimic an x cubed. This one will mimic an x squared. So the end behavior, just look at your x squared if it's a positive even. Just look at an x cubed if it is a positive odd. So if it says to describe the end behavior, this first one here is a positive even. So it's going to act like an x squared. So we can say that our left end goes to positive infinity, our right end goes to positive infinity. Now in example 3a, we have a negative x to the 9th. Now it is it's a positive odd, but we have a negative coefficient out front. So remember, that's going to flip it. So instead of going like a normal cubic, it has to flip over. So by recognizing that it's going to act like a cubic, except that negative in front is going to flip it. We know that the left end is going to positive infinity, and the right end is going to negative infinity. Let's look at 3b. Now we have a negative front coefficient, but we have an even power. So the negative front coefficient is going to flip it upside down. It's going to act like a quadratic otherwise. So the left end goes to negative infinity. The right end goes to negative infinity. So when they say describe it in words and symbols, that's all I need. The left end is going to negative infinity. The right end is going to negative infinity. So the basic summary is if we have an even, positive even power, if we have a positive coefficient, it's going to look like that. If we have a negative coefficient, it's going to flip upside down. So they all even power functions are going to look like parabolas. Now I'm talking about positive evens, 2, 4, 6, 8, 10. They're all going to look the same. What happens is that power kind of makes the center dip a little closer the higher it gets. So at an x to the 10th, the center will dip down a little bit lower, and the ends get a little bit higher, a little bit quicker. And then if you have a positive odd power with a positive coefficient, just think it looks like a cubic. With a negative coefficient, it looks like a flipped upside down cubic. Okay, so we should know those things, and so it's really important that we know that. So if we have a positive even power, think of quadratics. What does a quadratic do? Well, if you have a front coefficient that's positive, the both ends are going up. Front coefficient that's negative, both ends are going down. If you have an odd power, it looks like a cubic. If there's a positive coefficient, right end's up, left end's down. If there's a negative coefficient, left end's up, right end's down. Now, a polynomial starts out and looks like and behaves like a power function, but we have lots of terms added on. We could have lots of terms added on. Every single term that's added on is going to possibly create some bumps, some transformations of that function. But if we look at this function here, we're going to talk about what's called the lead term, which is that a n x to the n. N is your highest power, which we're going to call our degree. So our lead term is this highest power term. And all those terms look just like a sum of power functions. So 2x cubed plus 3x plus 4, that's a polynomial. 7x squared plus 2x minus 4, that's a polynomial. 8x to the 5th minus 1/2 x plus 3, that's a polynomial. Now, in example 4, it says identify the polynomials. Well, this one looks like a polynomial. What will look better is if we get it a little better. We smush some things together. So that's really 6x to the 4th plus 4. That's a polynomial. It has degree 4. And it will look like a quadratic kinda. It's been shifted and moved a little bit. Second one here. Let's distribute. We get negative x cubed plus 4x. The lead term is our negative x cubed. So the degree is 3. Yes, it's a polynomial. And it would be flipped upside down. So the left end would go up and the right end would go down. Now the 4x is going to create some bumps in the curve, but it'll still essentially look like a cubic. Now h of x is not a polynomial. Because it has a square root on it, we can't have a square root on our x's. It will start to act like a square root function, not like a polynomial. So the things you have to remember for a polynomial, the lead term is the term with the highest degree. The degree is just that highest power. The ends will act like that lead term's highest power, and just think, is the degree even or odd? If it's even, it's going to act like a parabola on the ends. If it's odd, it's going to act like a cubic on the ends. Turning points. Those are the hills, the valleys. So like if we look at something like that, that's a turning point, that's a turning point. Those extrema. The turning points, you could possibly have one less than the degree. So, perfect example. If we have a cubic polynomial, excuse me, where the highest is a 3rd degree, you could possibly have 2 bumps. Can't have more than that. You could possibly have 2. Okay, so those are some terminology I'm going to be using. So lead term is the highest power. The term with the highest power. The degree is that highest power. The ends will always act like that lead term degree. How many bumps could you possibly have? It's always, the most you could ever have is 1 less than the degree. So here it says, identify the degree, the lead term, and the leading coefficient. Okay. So our first one here, f of x. Our lead term is that highest power. The degree is 4. It is not. Let's try again. Our degree is the power, the 3. And that lead coefficient means that it'll be flipped upside down because it's negative. Our second one, if we look for the highest power, it's a 5t to the 5th. So the degree is 5. It will look like a cubic with a positive coefficient, so the right end will go up and the left end will go down. For h, the highest power is a cube. So our lead term is negative p cubed. So our degree is 3. That negative means that it's going to flip itself over. Now it might have some bumps in it. If you put that into, if you put any of those into Desmos, you should see this is what the ends are going to look like. Again, we're going to have some bumps. We're going to deal with the bumps as we go through this. So that's example 5. Let's look at this one. This is what you're going to see in Desmos. It says we have this polynomial here. Choose the end behavior. Okay. So the first one here, the lead term is negative 6x to the 4th. So the negative is going to flip over normally what a parabola does. So it's going to look like that. So it is going to fall to the left, and it's going to fall to the right. So it is going to fall to the left and fall to the right. And it's all based upon that highest power. For our second one, our lead term is 2x to the fifth. Don't assume that it's going to come first. Many times they're going to write it in correct order, but if it's not descending order, just look down your powers. What's your highest power? Now, an x to the fifth has the right side up and left side down, unless it's flipped over. This one is not flipped over. So let's start with the left side. The left side is going to go down, so it's going to fall to the left, but the right side is going to go up, so it's going to rise to the right. Okay, one more. Now this one's a little interesting. If you pull out all of the coefficients that are attached to x's and x's, let me just show you. If we were to multiply this out, the highest term is really going to be a -3 from that front coefficient. We'll just stick along for the ride, and then times an x, and then times an x squared. So it's really going to be the multiplication of those things. So it's going to be a -3x cubed, which looks like a cubic that's been flipped upside down. So you'll notice that it is going to rise on the left and fall on the right. So we want to rise on the left and fall on the right. So it's all about, if you were to multiply it all out, what would the highest power be? So just look at any x's, the front coefficient has to come along for the rise. That will determine if you're going to flip or stay in your normal kind of pattern. So that's those ones. It says describe the end behavior and determine a possible degree. Well, our left end here is going to -infinity, so it's falling to the left. Our right end is going to positive infinity. It is rising. On the right. So what possible degree could this be? Well, we cannot have a polynomial where one end goes in one direction, one end goes in another, unless it is a lead term degree that is odd. So it has to be odd. The degree must be odd. So what's a possible degree? Well, the degree might be 3, it might be 5, it might be 7. That's a possible degree. Now, I know for sure, because the right end's going up and the left end's going down, that it has not been flipped. So if they ask me about the front coefficient would be a positive coefficient. So let's look at this one. Describe the end behavior. So the left end is going to -infinity, so it's falling. The right end is going to -infinity, so it's falling on the right side. So both of these are going to -infinity. When they both go the same direction, that means that the degree must be even. Because they're both falling down, we would have to have a front coefficient that is negative. It says here, given this polynomial that's been multiplied out, or I'm sorry, factored, we're going to multiply it out and put it in general form. We're going to find the lead term, the degree, and the end behavior. Okay, so the lead term is just going to be the multiplication of those things. So it would be negative 3x squared times x, which is negative 3x to the fourth. Now, let's prove it when we put it in general form. So I'm going to hold off on that negative 3x squared, and I'm going to FOIL this out. So that's going to be x squared plus 3x minus 4 if you FOILed it out. And so our general form is negative 3x to the fourth minus 9x cubed plus 12x squared. So as you can see, that there is our lead term as I predicted. So what do we know is happening? Well, the degree is 4. It is going to be a flipped upside down something. It could have some bumps in between, but the left end is always going to go down, and so is the right. So the left end goes to negative infinity. It falls, and so does the right end. And you could put this into Desmos to verify that that's really going to happen. Let's skip this one. So here it says, below is a graph of a polynomial with real coefficients. All local extrema of the functions are shown on the graph. Use the graph to answer the following. On which intervals is the function increasing? Okay, so let's kind of mark that our function is going uphill until it hits an x value of 3. And then it's going downhill until an x value of 5. Then it's going uphill again until an x value of 7. And then for the rest of eternity, it's going to be going downhill. Okay. So let me just kind of write and then we'll highlight. Okay. So it's increasing, going uphill from an x value. Now remember, that's the word, what the y's are doing. The y's are increasing, the heights are increasing from an x value of negative infinity till an x value of 3. And then also there's a spot from 5 to 7. The y's are decreasing on all the other intervals. So it's going downhill from an x value of 3 to 5. And again, from an x value of 7 till the rest of forever. So the answers for the increasing would be negative infinity to 3 and 5 to 7. Remember, this is what the y's are doing. These are all x's. Okay. Then it says, at which x values does the function have a local minimum? Well, a local minimum is a valley, a low point, a sag in the graph. And so here at an x value of 5, we have a sag in the graph. So this is a local minimum. These two are local maxes. And those happen to be absolute maxes as well. It says, what is the sign of the function's lead coefficient? Well, we can already tell that the degree would be even because both ends are heading in the same direction. And since they're heading down, the coefficient has to be negative. So this would be negative. And then finally, it says, which of the following is a possibility for the degree of the function? Well, it has to be even. That's all we know at this point. It's either going to be 4, 6, or 8. Even functions always head, their ends always head in the same direction. This could not be an odd function. The lead term cannot be a 5, 7, or 9. I don't know much else, but I do know that. So remember, turning points are just a fancy way of saying relative max or min. The most x-intercepts I ever can have is the degree. That's the max possible. I cannot write today. Not that that's different than other days, but you know what I mean. The max possible x-intercepts will always be the degree. The max number of possible turning points, which I'm going to just abbreviate TP, would be the degree minus 1. So if the degree is 5, we might have 5 x-intercepts, but 4 turning points, 4 bumps. So if the degree is n, the most x-intercepts we'll ever have is n. We could have less, but the most we'll ever have is n. The most bumps, hills and valleys, turning points we're ever going to have is always going to be one less than that, because if it turns back around, we get another x-intercept. We can't have that. So here, if it says, without graphing, determine the local behavior of the function by finding the max number of x-intercepts and turning points. So this is how easy this is. The degree is 10. The maximum x-intercepts I'll ever have is 10. The maximum number of turning points I will ever have is 9. Now, that means the most I'll ever hit the x-axis is 10 times. It's rare that it's that many. The max number of hills and valleys I'll ever have is 9. I don't know what else. What is the ends doing? Well, the ends are going down. Example 7. Here's our lead term. The maximum number of x-intercepts I'll ever find is 5. The maximum number of hills and valleys I'll ever have is 4. What are the ends doing? The right end's going up, left end's going down. Now, for this one, you have to pull some things out of there. So it would be a negative x squared times a 2x squared for a negative 2x to the 4th. So my lead term is negative 2x to the 4th. So both ends are going down. The maximum number of x-intercepts I'll ever have is 4. The maximum number of turning points I'll ever have is 3. Now, will we be able to find all of them in this course? Maybe not. If you take calculus, there are some ways that we can find them. That's something we'll explore as much as we can, given what we can in a pre-calc class. Says, what can we conclude about the polynomial represented by the function based on its intercepts and turning points? Well, I know the degree is even because both ends are going up, the same direction. See how there's two x-intercepts. There's 1, 2, 3 turning points. So we have to have an even degree, but it has to be at least one more than the turning points. So the degree is even, it's 4 or higher. So it's 4, 6, 8. But I would bet on 4. Okay. Let's look at this one, this 11b. The degree has to be odd. Why do I know that by looking? Well, the left end's going up and the right end's going down, opposite directions. Degree has to be odd. It's hitting the x-axis in 3 spots, so there are 3 x-intercepts. There's 2 hills and valleys, 2 turning points. My bet, it's odd, it's probably 3. Could it be 5? Could it be 7? Sure. But it's at least 3, maybe 5 or 7 or higher. So we're just getting used to pulling apart a polynomial because eventually we're going to be able to graph them fairly accurately and fairly quickly. Okay. So it says, what do we know about the local behavior? So we're talking about hills and valleys. We also can determine a mixture of things. So let me show you. Okay. So the lead term is negative 4x times x, or negative 4x cubed. So the left end is going up and the right end's going down. I know that negative 4x equals 0 at 0. X plus 3 equals 0 at negative 3. X minus 4 equals 0 at 4. The most zeros I could ever find for a cubic is 3. I found 3. So look at how fast we can graph a fairly good representation of this graph. I know it hits the x-axis at negative 3, 0, and 4, right? Okay. I know that the left end goes up, the right end goes down. There had to be a bump and a bump and a bump. You throw that into Desmos, it's going to look something like that. Okay. Skip that one. So we're just exploring what is the degree, what is the lead term, what does it tell us? We're going to explore finding these zeros later on in another section. It's coming, okay? And then here's your homework that goes with it. And this one will be a really pretty quick one.